Hi, I'm Dr. Matthew Michael. I'm a lecturer of mathematics at NJIT. Um, I'm going through some of the Voice into Prima 10th edition PowerPoint slides to kind of help my students try to understand how to think and study and preparation for exams and the like. How to get them to understand what I'm discussing and meaning. So, remember that when we're talking about second-order systems, that the general form for a second-order differential equation is y double prime plus p of t y prime plus q of t y is equal to g of t. And mostly we've been solving the homogeneous that we see as a second equation. Today, though, we're going to start trying to answer the question, what do I do when it's not homogeneous? What do I do when the right-hand side is non-homogeneous? So that there is a g of t term that is non-zero. The method of undetermined coefficients is almost an ad hoc technique. It works. Be careful. It is very quick, but it is not necessarily the best. It is definitely a quick method, but it's very easy to make little mistakes. So please be careful what I am saying and what I am not saying. So, if we happen to have two solutions to the non-homogeneous equation, and we plug in the difference of the different solutions, a homogeneous equation, we actually get a homogeneous answer, homogeneous equation. This means that the difference between two solutions to the non-homogeneous equation is the homogeneous answer. That means that my solutions that are based on the g of t are unique to the g of t, and that any changes that you might notice in solutions will come from the initial conditions. So, like I said, y of t, that capital Y of t, which is going to refer to the particular solution for this particular g of t, and it will be specific to this particular g of t. And that c1 and c2 are going to be dependent on any initial conditions I may or may not have. Be careful that y1 and y2 are the fundamental solution sets for fundamental set of solutions for the homogeneous answer. So notice, even though we've branched out to non-homogeneous questions now, we are still going to need to solve the homogeneous as well. Now, the way we're going to go about trying to solve for capital Y of t, that particular solution, that's what we like to call it, will be a method of undetermined coefficients. We're going to determine the form of the solution type, and then we're going to determine coefficients in front of that particular form. So these solutions will usually take the form of a combination or unique to that particular type of polynomials, exponentials, trig functions, or some combination thereof. So you could have a polynomial instead of an exponential. Remember, that's repeated roots. We could have just polynomials. We could just have sines and cosines. We'd have exponential sine cosine. Remember, that's complex roots. But let's take a look at a simple exponential g of t. One thing that the slides are not discussing is that, first of all, we are taking a look and finding the homogeneous answer first. So if you take a look at the left-hand side, y double prime minus 3y prime minus 4y. What they're not saying here is that I need to determine what the homogeneous answer is first. So this would be r squared minus 3r minus 4 is equal to 0. This means my solution of the homogeneous or complementary solution will have roots dependent on r minus 4 times r plus 1 is equal to 0. So, in other words, my complementary solution, my homogeneous answer, will be, remember it was r plus 1 and r minus 4, right? So that means yc, or y complementary, or y homogeneous, is going to be c1e to the negative t plus c2e to the 4t. Keep that in mind. So now we're looking to satisfy a solution type based on my exponential g of t term, which is 3e to the 2t. Now remember, 3e to the 2t, that's an exponential solution, so that's a real solution type. That means that these solution types are literally e to the 2t. Therefore, my solution for capital Y of t will be some constant a times that solution type, e to the 2t. So plugging in y prime and y double prime into the original equation, we can actually solve for which particular a value will give me a constant of 3 after I've plugged it into the linear operator. Remember, we talked about those in 3.2 and the Wronskian and fundamental sets of solution. And it turns out that a is equal to negative 1/2, because once we plug in the solution y of t is equal to a e to the 2t into the differential equation, that's the only a value that will make the left-hand and right-hand sides equal to each other. Okay. Next, logical g of t. We started off with exponentials. Let's go to a different type, like say sine. Well, we still have the same complementary solution. Remember, that's yc is equal to c1 e to the negative t plus c2 e to the 4t. And now on the right-hand side, we see sine as a solution type. So it would make sense if I was to have a solution type of a sine of t. So plug in y is equal to a sine t, y prime is a cosine t, y double prime is equal to negative a sine t. Plug that into the differential equation and, oh, that's a problem. See, there are now sine terms and cosine terms, but all of it must somehow equal to 0. Well, the sine portion insinuates that 2 plus 5a must equal to 0, implying that a must equal to negative 2/5 a. However, cosine term is insinuating that 3a is equal to 0, or a is equal to 0. But that's a problem, because cosine and sine are not multiples of each other. They are phase shifts of each other. A little bit more complicated than that, but that means that they can't both be true. It's impossible, which means that we made an error. This is the kind of error that I'm saying this technique can be complicated about. And what we need to remember is that when we use sine and cosine as a forcing term on the right-hand side, a non-homogeneous part, remember when we talked about complex roots in section 3.3, we discussed how they came from the complex exponential, and that we had both cosine and sine that popped out of each one of those complex roots. Because both sine and cosine are both coming from the same root, whenever I see a sine and cosine show up on the right-hand side, if I see one sine, I have to use both sine and cosine. If I see one cosine, I need to include both a cosine and a sine. So in this case, when I see 2 sine of t, I can't just have a sine of t as a solution type. I also have to include a plus b cosine of t. Remember, the derivative of cosine is negative sine. So there might be some overlap. And indeed there is. Notice that once I include the cosine term, while it's not necessarily a friendly result, the coefficient of sine is negative 5/17, and the coefficient of cosine is 3/17. It now covers all the bases, because I have both sines and cosines that are intertwined. And so the effects complete that kind of space, kind of understanding what's going on. So in this case, when I have sine on the right-hand side, by including both a sine and a cosine into my solution structure, I'm able to solve it. This is different than the exponential. I just needed that one exponential. Whereas for sine, I need both sine and cosine. Remember, if I have a cosine on the right-hand side, include the sine as well. Okay? Last one, right? That's the other main case that we might see here. Maybe not last one, but another important one was a complex exponential. This was the imaginary with no real root. Here's complex, both real and imaginary. And like last time, we have a cosine there, cosine of 2t. So we need a cosine of 2t and a sine of 2t. This is perhaps one of the nightmare solution forms, because take a look at that y prime and y double prime. It is massive. Make sure to reduce the form down as best you can. When plugging that into the differential equation, it is going to be massive, but it is solvable. You just need to be careful. In this case, the coefficient of the e to the t cosine of 2t term turns out to be 10/13, and the one for sine and e to the t turns out to be 2/13. Remember, so this is a case where we had a cosine, but had to include the sine counterpart. So what happens if you have two terms on the right-hand side? Well, that means do the process twice. Just focus on each one individually. And if you add those up, it will work together. So we've solved this differential equation with complementary solutions 3 times, right? So using the different solutions for each one of those types and adding them up together, we get a full solution type. We just add all of our particular solutions together. So even though we've kind of done 3 examples now, by adding all the effects together, we've effectively actually solved one massive problem. Remember how I told you that the complementary solution was going to be very important? Here's where it kicks in. Notice on the right-hand side, we get an r value of -1. Here's a problem. Remember when we solved the complementary answer, y was equal to c1e to the -t plus c2e to the 4t. Remember that first y1? E to the -t. So that form is already in the differential equation. It's already in the left-hand side. That's part of the complementary answer. So when I plug that in, the left-hand of the side of the equation will already be 0 because I'm already taking in its effects. But this should sound familiar. See, I've already accounted for e to the -t, but e to the -t is showing up again as a possibility. So just like in section 3.4, where we have 2 solutions that want to be e to the -t, if we consider this second e to the -t in the particular solution, in the non-homogeneous solution, to be a repeated answer, a repeated root, well, that will help us form our type. And so repeated roots, remember when you multiply by t, so plugging that in, yeah, it's not the friendliest thing out there, but it will allow you to solve for A. This is one of those tricky parts about the undetermined coefficients method. I recognize a form and realize that it is a repeated roots problem. Because of that, I'm able to solve it. On the bottom right, you can notice a graph, what this might look like based on initial conditions. So, notice the second bullet point there. The most important first step is going to be solving the homogeneous equation first. Solve that first. Find that C1 and C2 right away. The second step is to find a form that fits the right-hand side to create a particular solution. Then plug in both that y of t, that y prime of t, y double prime, until you're out of derivatives, out of forms. Assuming that your guess for y of t is correct, your coefficients will be solvable. If it's not possible to solve for your coefficients, chances are you do not have enough or you have too many coefficients. Be careful. Also remember that if you have multiple forcing terms on the right-hand side, remember to do this process multiple times for each of those terms. Your final answer will be your complementary solution plus your particular solution. Hope this helps.